Okay, so I want to switch topics now from a discussion about virtual memory to a discussion about one particular aspect of virtual memory, which is page fault. So looking at this example, let's say we had a virtual address that ended up us getting to slot 8 in the page table. All right, so here's slot 8. Oops, here's slot 8 in the page table. Okay, when we reach slot 8, you'll notice that the bits that we would substitute as the prefix are all 0. And that's because the rightmost bit in the bit pattern that's kind of separated from the other bits has the value of 0 in it. So 0 indicates that we're going to have a page fault. Okay? It means that the physical page, which this virtual page should map to, the physical range of addresses that this virtual address range should map to, is actually not present. So that this chunk of memory, this chunk of virtual memory, is not in physical memory. So we have a page fault. And then we have to make a decision about which page of the existing pages that are currently in memory we have to swap out, so we can swap in the virtual page for slot 8 into some physical memory location. All right, so that decision about who to swap in, who to swap out is called a page replacement algorithm. That's what we're going to spend some time talking about. But first, I just want to draw a little flow chart here, a brief one, and then we'll look at a little more extensive one for what happens when we have a page fault. Oops. All right, so page faults. So there's two flow charts. I have a simple one and a more complex one. I'll show you the simple one and then we'll talk about the complex one in a second. All right, so a page fault's going to occur when you go to look in the page table. The MMU goes to look and it discovers that the virtual address maps to nothing. There is no physical address for the virtual address. And that's because we can't map all physical addresses to, or all virtual addresses, physical addresses to virtual addresses because we don't have enough memory. So some of them are not in memory. Some of the virtual addresses are not mapped to physical memory yet. Okay, so we're going to say a page fault occurs, happens. Okay, and when that happens, we're going to choose a page to swap out. Okay, this is called a page replacement algorithm. All right. After we've selected a page that we want to swap out, we have to ask a question about that page. Was the page read only? Okay, was the page read only? If the answer is no, then we have a problem. Because what it means is that the page that we like to, the page that's in physical memory that some other set of virtual addresses maps to has data that has changed from the time that that set of virtual data and virtual addresses was loaded into that physical page. In other words, there was some write operation that occurred. Okay, so we have to make sure that the data in that page doesn't get lost. The changes don't get lost. Right now on disk, we have a mapping from the virtual addresses that are mapped to the physical addresses. We have data there, but as the program runs, it might change data. So it's going to change the data in that physical memory location, and we have to make sure that the data in that physical memory location then gets written back to disk. Okay, so if we've modified the page that we're about to swap out in any way, shape, or form, we're going to write the page to disk. Okay. If the page was read-only, we haven't changed the physical page, we do not need to write it to disk. All right, and then we're going to read the fault page from disk, and we're going to stick that fault page in that set of physical memory locations that are now freed up because of the swap out. And then we just continue. All right, so fairly straightforward algorithm. The twist is if you're about to swap out a page, you're going to bring in a new page into that physical memory location. You have to make sure that before the swap out occurs, if any data is changed since the last time that page was swapped in, then you've got to make sure that that data gets written out to disk. Okay, so let's take a look at a more extensive page fault. I have a flow chart that I wrote here that I can share with you. So I'm just going to take a picture of it, and we'll stick it in the document for you. There we go. Okay, see if that turned out okay. Yeah, it turned out okay. All right, we'll just edit it slightly. Okay, done. And we'll send this to Notability. Oh yeah, let's put it in. This is quite an extensive document you've got here. Okay, we'll go to Notability. There it is, and we'll just make that nice and big, and I'm gonna just walk you through it so you don't have to take notes on this. But I think it's important for your own edification. Okay, so here's a more extensive explanation of the page fault algorithm. All right, so you've got some kind of load operation or store or whatever. All right, and so let's get a better, I like purple. There we go. All right, so we're going to do a lookup of XXX, the virtual address, in the page table. And if it does not fail, then we're just going to convert it to a virtual address, convert the virtual address to a physical address. If it does fail, it means that we are unable to match that virtual address with a physical address because the mapping's not there. We don't have a page available for that range of virtual addresses that the XXX falls into. So we have a page fault. So the first thing we're going to do is we're going to save the state of the process. And then we're going to go and do some other work other than running the process. Basically, the operating system is going to go off and do some work. So the process, in effect, actually, the process goes into the blocked state. All right, so do we have a valid virtual address? If the answer is no, then kill the process. If we have a valid virtual address, are we allowed to look at that memory location? In other words, are we looking in an area we're not supposed to be looking? So if the answer is no, we're not allowed, we're going to kill the process again. Okay. Is there a page free in the page table? If the answer is no, we're going to have to do a page replacement algorithm. All right, so page replacement algorithm, we're going to end up selecting a page to swap out. All right, is the page dirty? Dirty means that we wrote to the page. The change has been made to the page since we last loaded the page into physical memory. Okay, if so, we're going to write that page to disk. And while we're writing, we're going to say, is the IO complete? And we're going to be in this loop. Is it complete? Is it complete? Okay. Yep, it's finally complete. All right, if it's finally complete, then we're going to read the new page from disk. This is the page that contains the address XXX. All right. And we're going to say, is the IO complete? No. Okay, we're going to keep doing this until we finally read the page. And once we've read the page, we're going to go to A. We're going to update the page table. We're going to restore the process state because now the process is no longer blocked. And then we're going to wait. We're going to go into the ready state so the process can begin executing again. So that's a much more detailed explanation of what happens when a page fault occurs. So I hope that helps you understand page faults. Okay, so what we're going to spend the most of the rest of our time on then is we're going to spend the rest of our time on this, the page replacement algorithms, because it turns out that, you know, I think the idea of virtual memory, I'm hoping that the idea of virtual memory makes sense, but it has this situation. You're taking something that is enormous, an enormous range of virtual addresses, and you're mapping it into a finite, much smaller range of physical addresses. And you aren't always going to have that mapping. So sometimes you're going to have to do page replacement. So the question is, how do we decide of all the pages that are chunks of physical addresses where virtual addresses are mapping those physical addresses, which page should we swap out so we can swap in the set of virtual addresses and data that we need to work with into this page frame? All right, so there's a bunch of ways to think about this. So the first way is we can get kind of theoretical to make life easy, and then we can talk about other techniques that are more practical. So the first technique is called optimal page replacement. So optimal page replacement. So we have a page frame. And this represents a range of addresses. So let's say like this is 0 to 4K, okay? And we have a little box here that says how many instructions until this page is needed. So let's say there are 4 million instructions before this page will be needed, okay? And now we have another page frame here. There are 8 million until this page frame is needed. So this may be 4K to 8K. And we'll just draw another one here. Maybe there's only 100,000 instructions before this one is needed. We'll do one more. And maybe there's only 30 instructions before this one is needed. Okay, and we can continue on like that. Okay. So if there's a page fault, which page would you select to do the page replacement on? All right. So when the page fault occurs, it means that there's some virtual address that cannot be mapped to a physical address. So we have to select one of these page frames, one of these 4K ranges to swap out, and then swap in the 4K range that includes the virtual address that we're interested in working with. So if you look at this, you know, it seems pretty obvious to me which one we'd want. We want to swap out the page that is going to be needed furthest in the future. Okay, we're going to need this this one in 30 instructions. We definitely don't want to swap that one out. 100,000 instructions, we don't want to swap that one out. These 4 million, 8 million, those look like possibilities, but 8 million is really far off in the future. And so we're going to swap out this one. Okay, so what is the flaw in the page replacement algorithm? It seems like pretty obvious, right? We know this one is going to be needing 8 million instructions, okay? So what's the flaw in the algorithm? If you think about this for a moment, how the heck do we know how far in the future these pages are going to be needed, right? We don't have a crystal ball. We don't have a time machine that we could use to go in the future and say, oh, the 4K to 8K page is going to be needed in 8 million instructions. Now, that is very true. So that's sort of the fatal flaw. Oops, fatal flow. Fatal flaw. How can OS know when page will be used next? Okay, so that's the fatal flaw. Okay, and the answer is it can't, it really can't. However, in simulations, we can determine this. And get a best case scenario for future research, for research purposes. Analysis. But it's not really good in the real world. This is not possible in the real world. Okay, but it's useful to know what the best case scenario is, what the optimal page replacement is. If you want to compare other page replacement algorithms to the one that you devise, or sorry, if you want to compare a page replacement algorithm that you devise, what's your basis of comparison? Well, you can use this optimal page replacement as your basis of comparison. This is the best you can do. It's just that you need a time machine to know that. So like in a research lab, it would be really useful. But in the real world, it's not so useful. Okay, so if we can't use optimal page replacement, maybe we can do something else. So how about this? How about this one? First in, first out, FIFO, page replacement. Okay. So essentially, what we're talking about here is when we have a page fault, the key here is when page fault, swap out the oldest page. All right. The first page that you swapped in will be the first page that you swap out. That's why it's called first in, first out. So I'll just write that. First page you swap in will be the first page you swap out. Okay, so is this a good algorithm? Well, first of all, this is something that could definitely work in the real world, right? We don't need a time machine to do this. We just need to keep track of what is the first page that we swapped in when we started managing virtual memory for this particular process or set of processes. Okay, if we know what that page is, when we have a page fault and it's time to do the swap, we will select that page as the page that gets swapped out. So in terms of practicality, we could definitely make that work. Now, is it a good idea to do this? Is the oldest page the best page to swap out? Well, there's something to be said for getting rid of something old and bringing something new in, but old is not necessarily bad. If you have a page which is used a lot, like let's say it's the page where your main program happens to be located and most of your code is running in your main program. And so you're frequently accessing the memory locations that are in your main program, even though that may be the first page that was swapped in when your program started running, it's also the most popular page. So maybe it's not a good idea to get rid of it. So the answer here is probably not. Old does not necessarily equal to be unpopular. Okay. You can be old and popular. All right. So if first in, first out is not the best, although it's practical,